Today I'm going to present you a CAD tool named as ConsolidDesign, aimed at supporting part consolidation designed for additive manufacturing. First, let me explain what is part consolidation in additive manufacturing context and what are challenges to be solved. A part consolidation belongs to one of the design freedoms enhanced by additive manufacturing. Additive manufacturing is a layered process to fabricate parts by addition. With additive manufacturing, designers can have more freedoms of highly complex shapes, multi-colors, or multi-materials. Meanwhile, designers can integrate multiple parts into a more compact component without assembly operations. The last aspect to keep in mind is that AM still have its constraints. The most famous example of part consolidation in AM is the GE fuel nozzle, which consolidates 20 parts and reduced 25% weight, but made it 5 times more durable. Another more complex case study was also introduced by GE with nearly 900 parts consolidated into 12 components, shortening the lead time by half. However, the know-how of the cases is confidential, and they are highly experience dependent and labor intensive. In part consolidation research, the most critical challenges are to solve problems of which and how. In problem of which, to identify the parts candidates out of a complex system, such as an octocopter, is labor intensive. More importantly, the decision rules for such purpose are not well established. In a problem of how to fuse the parts into components is not to simply merge the parts by eliminating fasteners. However, methods to support part fusion are under development. The methodology. To solve the two challenges, a redesign method is proposed. It consists of 4 modules: function analysis, screening, embodiment, and refinement. The function analysis module is to extract necessary information for supporting part consolidation decisions, such as function structure and adjacency information of parts. The screening module is the step to find the candidacy paths for consolidation with inputs of established rules, where the embodiment step is to fuse discrete parts into one single component. The final step is to further optimize the consolidated part with other techniques such as topologization or lattice design. Among this, the first and last module have been well investigated by other research. Therefore, these modules are not covered. The unsolved challenges lie in the steps or are bounded by the relevant. The tool is developed based on Rhino series and its SDK. To load the plugin, you need to use the command line plug manager, find the plugin file. After it is successfully loaded, you can use it instantly by typing in the command line as ConsolidDesign command. The interface will pop up, and you can see it has 4 main drop-down menus. In the first place, you need to load the CAD file, and it has to be 3DM file, since you need to explore the material information. After CAD model successfully loaded, and you need to go to the info setup menu to start a new session to acquisite enough information of the part. In info setup editor, users are asked to perform function analysis with some direct instructions. First, this tool can automatically generate the product tree with labeled numbers. It also provides a function to explore the assembly for easy visualization, or you can choose to collapse the explosion. By double-click each part, it can automatically extract the information such as the material information and the bounding box information. But for certain information, for example, is standard information, you need to manually input. and also the maintenance frequency. After extracting the information, it was saved into an XML file. I will show it in the end. The next step is to extract functional information and the adjacency information of each component. For example, component 1 here is the red casing. It's a red casing. It fulfills a function of carbosolid, and it also adjacent with component 4 and 6. The next step is to define the function relationship between these components. For example, for component 4, it is set to exchange large force and form physical connection, but there is no relative motion between these two components. And for the next, for left casing, the purpose is to exchange signal, and there is no physical connection between these two components, and there is relative information between these two. By doing this, it defines the interaction relationship between different components, and it can establish the interaction network between the parts. By repeating this operation for all components, and it will finally establish the function interaction matrix for the whole assembly. By following the XML scheme, all the extracted information will be saved in the predefined data structure as shown in this file. This file will be reloaded for the next step of automatic detection of candidates for part consolidation, which will be introduced in the next slide. When the function analysis module is finished, the next step is to do screening to find out which parts can be consolidated. As shown in this slide, the general procedure consists of 4 steps as FPI network, module division, community detection, and finding the feasible maximum subgraphs. The cornerstones of this method are design structure matrix, module division algorithm, and part consolidation candidate detection algorithms. The general idea is to model the physical assembly by virtual network so that mathematical computation becomes feasible. Previous function analysis module is corresponding to the FPI network in a matrix format. The established rules and principles are encapsulated in the steps of module division, community detection, and feasible subgraphs are implemented in the screening module. Let's look at how the screening procedure works. The first step of the screening module is to reload the XML file with the predefined information. And then the second step is to go to the screen module and choose find primary groups. As you can see in this pop-up window, the screening process requires 3 steps. The first is to set up the AM constraints because we need to consider the manufacturability of the printers. The second is to set up the parameters for the automatic algorithm for part consolidation candidate detection, and the last step is to define the result. First step, you need to select the 3D printers, which is predefined in this system, and you can also customize the constraints by adding new printers. And you also need to set up the output directory. In the PCCD parameters, you need to set up the product scale, the module division algorithm, and also the modularity threshold. In this study, we have 3 scales: product, module, and assembly. Product refers to a highly complex system, for example, an engine. The second is a module, which refers it is one modularized unit in a highly complex product. For example, this gas pedal is a module, and an assembly refers to a unit of a few components. Then you need to define the module division algorithm. By default, it is the GA Govan-Newman algorithm for community division. And also you need to set up the modularity threshold at 0.3, which is a recognized value in the social network study field, and we borrow the concept for this purpose. It means if the modularity value is larger than 0.3, it means there are communities within the network, and there's a need to do module division and community detection. After all these parameters are set up, the algorithm is able to automatically calculate which components are suitable to be grouped as one candidate for consolidation, and you can visualize the result by coloring it in different colors. For example, the components colored in purple means that these components can be consolidated as one part, and also you can visualize the result in the statistic window here, and you can see 1, 2, 3, 4, 8, 11, and 14 are supposed to be consolidated, and the other group is 5 and 6. However, we found that the component 8 and 11, they cannot be consolidated because the consolidation of these two components will affect the insertion of a third component. Therefore, they need to be cut. Then this grouping solution need to be recalculated, and you can visualize the final result for this case study. The computation time for this calculation is around 38 milliseconds, and you can save the result, and you can proceed for the second step of embodiment design. The next module is the fusion of parts, which is also known as embodiment module. In this proposed approach, three concepts need to be clearly understood: function interfaces, function volume, and initial design space. Function interface are the surfaces that interact with external environment or assembly interface. In this example, the green channels convey fluid, and the surface in blue coupled with external columns. Function volume can be seen as the interface with minimal thickness to undertake stress. The initial design space can be seen as the solid that encapsulate all the function volumes. Overall, the general flow of the proposed method is to extract all the function interfaces of each component and check whether there is possibility of upgrading the function interfaces with AM design freedoms while satisfying AM constraints. In the end, it produces a consolidated part. Embodiment design here refers to the fusion of components selected as a candidacy group. In this developed version, embodiment design, there is only one function called redesign, and most of the procedure is manually done, and this user interface is only used as a guided step to direct users how to fuse these components by extracting the function interfaces, and also ask if there's a need to upgrade this kind of function interfaces. Then it will generate the function volume for each function interface and connect all these function volumes as an initial design space, which can set up the potential for seamless connection with refinement such as topology optimization or lattice design. As an example, we choose group 1 to proceed. And you can see group 1 is isolated from the rest of the other components. The first step is to establish function interface mappings. We choose the red case as an example. The front face is selected, and it is a part interface because it's an assembly interface with the left case. And you can also add its function as couple solid. And we also define the second function interface as its back plate. The function of the second function interface is the part environment because the back surface of the rack casing is to separate dust. When it is completed, you can see the extracted function interfaces. As a predefined procedure, we extract all the function interfaces in other software, and this only shows you how it looks like when all the function interfaces are extracted. And you can see different function interfaces are extracted and represented in different color. The yellow represents the boundary surfaces. The next step is to specify if some of the interfaces need to be upgraded or fixed. For example, the obsolete screw holes in the backplate of the rack casing. And so you need to choose the function surface too. And by this time, you can see the repaired function interfaces. The next step is to determine the best building orientations, considering the priority of different function interfaces, which need to be preserved in the building process. In this demo, this function is not well developed, but this research has been intensively investigated by other researchers. And since this case study is very simple, the Z direction is the best building orientation, and we can define it as the optimum building orientation. The final step is to generate the function volume for each function interface, which is predefined in other software, and this should only serve as a demo purpose. And you can see each function surface is secant into a function volume. The final step is to join these function volumes into initial design space, which serve as a solid for load bearing. According to the criteria defined, whether the function volume needs to bearing load, and also how many function interfaces is calculated. Then it will choose different methods to generate the initial design space. Interested readers can find the definition in related papers. In the end, it will generate the initial design space to link all the function volumes. Repeat this procedure for the other group, and you can define all the function volumes and initial design space for the fused components. The final step is for refinement, which provides an interface to link to other softwares, for example, topologization or Intralattice, which is an in-house developed software in ADML lab. The general purpose is it provides seamless integration from assembly design to part level design, which enables the maximization of the design freedoms of additive manufacturing and can enable a high level of design automation. Currently, this module is still under development, and interested readers can follow up in our website. Interested readers can expand their reading with the following publications. And also for further inquiries, you can send your questions to Dr. Sheng Yang, as you can see the email address here. Thank you.